Hi everybody, just after that introduction to let you know that I'm actually based in Colorado, so I traveled here yesterday from there, but if you can't tell by the accent already, I come from a land that is now famous for lack of skill in breakdancing, I think, now, so just so you know.
Oh, New Zealand.
Yeah, right. Yeah. So today I'm going to focus on a few areas. One, about the demand for prefabrication, how some of the field technologies can help in that area. I'm going to show you how we connect different data from the office into the field and back again. And also show you some examples of actually people using this technology and the results that they get from it as well. So let's talk a little bit about the demand for prefabrication. So based on industry studies, of course, some of these things that you probably know very well, that's really pushing prefabrication and modular design. So of course, one of that is scheduling. There's always constant pressure to make sure that we get things done on time. And I think that the on-time thing just depends on your perspective of what's on time and when you actually get started. So it's a little nefarious about that. And I think the industry gets a little bit of bad play on that, because people start schedules after they have an idea in their head and not actually when actually things get scheduled, get actually put out and bidded on and then actually accepted. So it's a little bit different. We all know about the lack of labor and the lack of skilled labor, and it's a constant battle to get that. So technologies can help in that area. There's a lot of competitive, not only about pricing a job, but also the cost of goods have escalated in the last few years to a much higher degree. So having prefabricated components and having some consistency about cost can help out there. Some of the owners now requesting prefabrication. I'll give you some examples of that. I would say data centers is one of those, where people like Google, Microsoft, AWS are all pushing for prefabricated components based around knowing of how things are going to get constructed in a very succinct manner. And also I would say things like new construction hotels are very much fabricated and put together as well. And then also engineers and architects are now looking at prefabricated pieces. I just sat through a presentation on steel structure and how important the prefabrication of large components can be for buildings. So when it comes to prefabrication services, I would say that we've been doing it for quite a long time, especially if you look at the mechanical, electrical, and plumbing trades. They've been doing a lot of prefabrication in their workshops, putting a whole list of components onto a truck and out to the side and trying to make sure that they can put them together and ensuring that they have consistency and repeatability of what they're doing. You're starting to see more and more kitted services, that is putting pieces together, whether it be off-site or also an on-site yard, putting pieces together and bringing them onto site. And then, as you can see in that picture, now getting much more coordination, and you're getting more multi-trade type of assemblies putting together as well. And then you have the full modularity, where you have a whole component that's put together, brought onto site and lifted into place. So that's when it becomes critical that you have technologies to make sure that these components are going to fit. So let's talk about some of these technologies that can help you out and why they're useful. So at Trimble, I put them into 3 different categories. One is field layout technologies. That includes both total stations and GNSS components. So if you didn't know, Trimble was the first company that produced commercial GPS. So we have a long history of that. And total stations, of course, have been used for centuries by surveyors to put things into place. We've taken them and put them in the hands of contractors to be able to execute and do things efficiently and accurately, much better than string and tape, for instance. Probably one of the most recent technologies is what we call extended reality, which includes augmented reality and also mixed reality. So augmented reality is something that you hold in your hand, runs on a tablet or maybe on a phone. Mixed reality is where you wear a headset and you're fully immersed in the area. So that's something like the Microsoft HoloLens. And then we have reality capture, and that's where 3D scanning technology. For a lot of people who don't know, reality or 3D scanning technology has been around since around 1992. It started out with a capture of data points at around about 70 points per second, so you could actually watch the dot go up the wall, to today where you have 3D scanning technology that's scanning at like 2 million points per second. So a lot of data capture and a lot of progression of information that you have to manage as well. So when it comes to things like total stations, as I mentioned before, it increases both the efficiency and accuracy at which you can place components or specific points on the ground to be constructed. This is a real world example, just showing you that a single person can be much more efficient on a job site, and it not only can produce better results, but also you can see that it can save you a large amount of money. And that's part of the structure that was calculated off, just so you know. So it just depends on the site, the height, and the width of the structure, obviously, depending on how much money that you can save by using this technology. When it comes to augmented reality, you're starting to deliver a lot more context to the job. So you can take in your hand, essentially, 3D design model and lay it over in the real world. So basically what you do is on a 2D screen, you get a 3D model overlaid on the real environment. So this gives you a lot more context to what is going on. It also makes it much more intuitive to interact with, because you're just using a screen that you're used to using every day. And it also has a lot of interaction with the model. So you can click on the component on the model, you can get all the BIM data as much as you like about it. Not only the information about the component, but also the scheduling, the costing of it as well. And then as you scan around and move around, it's using the sensor technology that's built into your tablet or phone. And then it's moving around, mapping the environment, and then overlaying the model as you go along. So into this technology or in the software, it's also built collaboration tools. So you can actually mark on there things where you see maybe some clash items. You want to indicate to the engineer, we need a change in this environment. If you have some internet connection, you can have real-time feed of that data back to the cloud, where somebody can get a notification and start working on that in real time, near real time, I would call it. So this gives you an idea of just a small structure. It's in a mechanical room, seeing that a component needs to be placed, a new component needs to be placed into the environment. So you can see that you get a one-to-one scale of the component into this real environment. So you can see the model, and you can also see, what actually is built at the time. It helps here for validation. You can communicate back to the office. You can actually take a screenshot of a single location and mark it up. And you can also have many, many different formats of models that you're using depending on where you authored the information from. Now, when it comes to reality capture, as I mentioned before, you have a large speed of capture. It's very efficient for collecting lots of data. It can collect all sorts of different surfaces. So it's very easy to measure from, say, wall to wall, or maybe beam to beam. But it's not very difficult to measure something that is curved and very ornate, for instance. So if you have a very old building which has lots of ornate components to it, it's very difficult to measure that in some other way unless you do some sort of photogrammetry where you're taking lots of images. Or maybe you have a very intense design that has lots of curved walls or curved beams. It's very good at capturing that data because it's all in 3 dimensions. Because you can capture the data fast, you can actually interact on the screen with the data. You can overlay the model, so you can actually do some quality control checks as you're going along to make sure that what is actually being built conforms with the design. And by collecting all the information, it also allows you to have lots of digital data which you can then archive and also create lots of reporting from as well. So we capture all this data. How do we communicate it back and forth? That becomes very important because then you get this near real-time sharing of information because we're always collecting the information digitally. Rather than, I would say, many years ago when I was working on construction sites, everything was on a plan, you're taking notes. That information tends to get siloed and doesn't get really shared. With digital information, it's much easier to share. You can email it, you can sync it up to the cloud, you can email it to people, so it's much easier to share the information, and also you can reduce the siloing of information between different parties on the job site. So how do we do this today? I'll talk about what Trimble has, but there are many different other ways that you can do this. We have an environment called Trimble Connect, which is basically an environment where you can aggregate lots of data. You can share to-do items. You can also share reporting. You have 3D visualization. So that's just one of many of those type of solutions that are available today. It's a very agnostic environment where you can put all sorts of different data. So it can be anything from a 2D plan, a 3D model. It can be just singular point data. It can be 3D point clouds. It can be lots of images. So you have a very varied amount of different data there. It gets automatically archived, so you can go back and look at the archives about what has happened. So if an issue comes up, it allows you then to go back and look at that archive. Where did that go wrong? Let's not repeat that for the next time that we do something. So it's good to have that archived information. It's very strong visually because you can have different views. You can share those different views amongst the parties that are using the information, and you can have it accessed by anybody. So to actually view data, it doesn't cost you anything to view data. If you want to upload and share different data, the different solutions have different costings based around what your access is. So this environment allows you to take data from different sources and have integrated workflows between these. So not only does it have data that you can post there, it allows you to then bring data back. So as you get more and more data added, it allows you to have alerts for people who are using the different environments to say, okay, you have a new update to this model and you want to share it. We want to have more people working on it. Or here's an issue, we need to have some sort of conversation about how we want to make a change to it. And also we can share this data out into the field and share the data back from the field. So I talked about basically on a tablet, you can have all this field data connected to different sensors that either collect data or actually propagate the data out so that I can then mark it out in the field. So then all the workers can construct that information. I can go out there as, say, maybe a site supervisor using my augmented reality, making sure I'm doing checks on the work that people are doing. Or if I catch it with a 3D scanner, I can then share that information up to everybody onto the job site. This information also can be shared to, I didn't mention before, construction robotics. And I think at the same time, there's a talk on construction robotics. But things like Spot the Dog can go out there and collect 3D scan data. You can also collect images. And what it can do as it collects that data, it goes back to a docking station, hits that docking station, and automatically downloads the data and shares it up to that connected environment. So that's being done today on some job sites. The other one is a site print layout robot, which takes the layout information, say, for your interior walls, and goes ahead and starts marking out all those locations automatically. So you have this data being shared in some form of robotics that are happening on some job sites today. I wouldn't say that it's widely used today. It has a long way to go for it to be much more accepted. So let's look at some examples of where people are using these different technologies to get some results. So I couldn't put the customer who's doing this work, it's a little bit sensitive, but this is at the Atlanta airport. And if you didn't know, Atlanta airport is the busiest airport in the world. So doing any sort of work there is going to come with some sort of cost and take a lot of coordination. So currently they're doing Concourse D to do some upgrades to the terminal. They want to expand it a little bit and also widen it as well. So one of the problems with being the busiest airport in the world is if you have a shutdown of that terminal, you're talking about $3.2 million a day in revenue that is lost. It's a huge amount of money. Over the course of a year, that comes out to $2.3 billion. So we don't want to have to do that. So what they did is they came up with an idea of doing prefabrication of very large components, which you can see one of right here. And so what they did, they have a on-site yard, and they're constructing these large pieces ahead of time. And they specifically built, you can see here, a special trolley that will lift it up and pull it along and put it into place. So what they do, they're using robotic toll stations and 3D scanners as they're constructing this to capture data and also to position it, accurately position it. So what they do is they construct it and then they bring it onto site. So I have some images of that. So you see what they did on the far left. You can see they actually built a 3D model. They mapped it out in SketchUp and then figured out how they were actually going to do this. So they used a 3D model, actually 3D printed it and figured out how they were actually going to do it. And then the bottom left is actually, you can see the tablet with the 3D scan data. They scan both the terminal and also the structure that is on this on-site yard to make sure that all the components are there and that they're going to fit together. Then on the top right, they use the robotic toll station to do spot checking of where the pieces are going to fit to down to the millimeters. And then the middle one, you can see there's a small window where the early hours when the airport is actually shut down. So they take the component, they put it on this trolley, and they move it out to the side, and they position it into place. So you can see the middle picture is it actually positioned into site. And you can see obviously lots of people admiring the finish of the work here. So they're doing this section by section on the job site. Another application is in a data center. So in this case, they had a big issue of actually people sharing data between trades and making sure that everybody knew what the other person had been doing on the job site. So what they did, they are using some positional technology to make sure that things are put into exact locations. But the problem is, as I mentioned before, they were siloing data before, and that was costing other people time and effort because they didn't know what was done previously. So they're taking this information, they're using robotic toll stations, positioning, capturing, doing quality control checks. But the big difference, what they're doing now is actually sharing that data in this connected environment so everybody has access to it. So it's saving them lots of time and money when it comes to the next scheduled person along the way. And then in this case, this is a naval base in Norfolk, Virginia. So they have multiple trades there. In this case, this customer is an electrical contractor. They're doing lots of prefabs and installs on this job. The one problem for this electrical contractor, they're generally sort of the last person that is thought of when it comes to actually the trade installation. So they need some flexibility about how they do their work and how they design their work. So what they're doing is they go on site with their robotic toll station, they capture what is actually being fabricated at this moment in time. They take that information, they check that with the design that they have put together, and then they make adjustments based on that so that when they go out to site, it all fits into place in a much simpler way. So they're using a bunch of different solutions to make sure that they guarantee when they go onto site, nothing's going to interfere with what they're doing. So moving away from the actual job site to maybe in a fabrication shop where you can use two of these technologies combined together to erect large steel pieces. So here, this company is, there's a group of companies, there's a design firm, there's a shop firm, and they're using different solutions. And so they're putting together these large components. So, I wanted to point out, so you can see the laser scanner there on the left-hand side. They put it in different places around the shop. They have the robotic toll station. You can see it way up at the top here. They have it constantly set up there in the shop so that they can then make sure that they work on the job, on the coordinates they're designing to, they double check that for each component as well. So they spot check that with the total station. So what they do is they take a model. This one is done in Tekla, but it could be in any other authoring software as well. They create that information, they put it together, they load it up to the cloud. The guys in the shop can download onto their tablet. And so they have the model in the field. And then they start using the 3D, the two technologies together. So this is a screenshot. This is actually a shot from what you see on the tablet. All this data that you see here is all small dot data. This is all 3D scanning data. So you can see it captures the whole shop, but the most important component is the one lying on the floor, obviously. And you can see the green lines. The green lines is actually the model itself overlaid on top. So it gives you an idea of what you can actually see on a tablet. A lot of high fidelity data. So what they do is they take some time to set up. They do a component-based setup on each little component. So they use 3 or 4 or 5 different points they can reference to. They align the component in the view, in the sort of orientation that's set out on the floor. And then they scan the data. So what you can then see is 3D scan data overlaid on the model, and you can do then a full 3D comparison. So you can then see where it's warping, whether the right pieces are in place. And then they can do that and take singular measurements off it, comparing the two. And they can verify everything's in good order or not, or make changes. Then they can actually share it back to the office. In the office, they can use their authoring softwares to do a much greater comparison. So all the people back in the office, like the engineers, they can look at it, they can look at all the components, they can do the comparison to ensure that it's meeting the specifications that they had set out and designed to. So here again, this is this near real-time sharing of information before this gets put onto a truck and goes out to the site. So this is something that the customer put together about the savings by using these technologies and the cost savings that they're getting based around a large number of components by using this technology. So it's not only one that it's key related to making sure things are correct, but it's also here you can see that it's also saving lots of time and money based around not getting things wrong. Here's an example of using augmented reality technology. So this is a new construction of an apartment complex. You have all these plumbing components are being put together. And what you can do with the sensors, the LiDAR sensors that are in your phone or your tablet, is you can turn them on and you basically capture what I call light scanning data. So that's what's happening when you see the animation there. And then, so this is this case here. It's capturing that information. So because you have the model and you can see the comparison in the middle shot there, you can see the difference between where the pipe is and where the pipe is and where it was designed. So you can see here it's like 350 millimeters or something like that out. So that's in feet. This example was in the US. So you can quickly see, is this something that we can put up with? Or is this something where we need to make some changes? So we can quickly see that before any major changes happen. Also, this data can be archived. So in the future, if there happens to be some sort of leak, we know where to tear down the roof and make sure, or tear down or dig up the concrete to find out where that pipe is. Here's an example from New Zealand. This was a remodeling of a theatre. And they have a lot of components in the middle there that they're changing. So the building was quite an old building, and they needed to update not only the interior design, but also all the mechanicals as well to be able to accommodate a much larger space that they were building. So they're using the augmented reality capture information, placing it on the model of design, and then doing the comparison. This is a in-shop environment, obviously. This is John Jones Steel Company. So what they're doing is the shop superintendent essentially is using augmented reality solution here to check on what he's doing. So he has lots of shop drawings here, but things are busy and he wants to be able to walk through the shop very quickly to make sure that things are running and being done as per design. So what this allows the shop superintendent to do is they can do visual checks quite fast and quite intuitively. So it can overlay the model. It can quickly line up. What they do is they put down some RFID tags, not RFID tags, some just scannable tags on the piece of steel. It automatically aligns it. And then you can walk the length of the piece of steel and make sure all the components are being put into place. You can see some of the components can be quite complex, so he wants to make sure that it's being done as it's laid out to be. So it helps these complex assemblies. You can quickly see that in a very visual way rather than have to look at the drawing, make some measurements, then move to the next piece. You can just quickly walk through the whole environment. So I didn't need it all the time, obviously. So I hope that gives you a good overview of how these advanced technologies can help both on-site and also in the shop to give you a lot of not only the ability to understand what's going on, but also then to share information and make much more informed decisions as you go along. Any questions?
Do you have any companies relatively local that are using the robotic layout, either for demising walls, mechanical, even structural walls?
Yep, I think there's a long list. I don't know them off the top of my head, but I can get those for you. You want to talk to some of them to understand how they're doing it? Yeah, I can definitely do that for you. Yeah.
In terms of the prefabrication, when you're working on plants to produce these elements, and at the same time you are doing work on site, there's a feedback that could be leveraged with this platform and these tools, right? In your experience, the particularities of the materials, steel, even the weather conditions, or things that could affect, have been brought back and have been utilized in this example?
Yeah, so in that steel prefabrication, that happens a lot because in some cases they have maybe it's an on-site design shop, so they can share that information directly back to the office. Sometimes that location is further away, but they're sharing that information directly today in this cloud environment so that they can quickly see if there's any sort of, like the shop supervisor, he can quickly make a decision, but if that information is being shared to somebody who can look at it in more detail, then they can make some quick decisions if need be. Yeah, that's the biggest advantage of using these newer technologies now.
How long does it take to align the model to the scan?
Yeah, as soon as we, when you set up, so the three different technologies, so with the robotic total station and the 3D scanner, we measure some known locations. That automatically sets the 3D model into the correct orientation, and so the data that you then collect is automatically lined up.
So back to the structural example you have there.
Yeah.
They would start fabricating that beam. Do they first have to use total station to identify where it is on the horses?
No, not necessarily. So like this, if I go back a couple of examples, this one here is what they can do is you lay down the main pieces, then you take a few quick measurements. Now, the 3D scanner also has the ability to measure some singular points as well. And so it then orientates it to that, and then you line it up there. If you need to, you can reorientate very quickly if they decide to move things, you can reorientate on the fly.
Is this a 5-minute process, a 10-minute process?
5-minute process.
Yeah.
Roughly.
Yeah.
So it becomes very immediate, like things that you need to do, and it's much faster. You don't have to go back to the office, you don't have to mark this off, bring it back to the shop. Yeah,
exactly. So if you compare that to way a lot of people do it, is you're measuring with a tape measure with a string, you're writing things down or entering on the plan. Sometimes that gets shared back with somebody, sometimes it doesn't. So it takes somebody to make sure that these guys are doing it correctly. So now that with digital data, it can be automatically shared. If you have some sort of internet connection, it can be automatically shared in real time. Yeah.
So that stiffer on that plate there, if you
Yeah.
had a scan, could you trust it within 2, 3, 5 millimeters?
Yeah,
Pick what number, was it 2 millimeters or 5 millimeters?
I would say 2 millimeters.
Okay.
Yeah. At that range, 2
Yeah.
millimeters, yeah. Yeah, if you had a very long piece,
Yeah.
then you would probably have multiple setups just to ensure that accuracy changes. Yeah. That could change as the things expand and contract, of course.
Yeah.
Yeah.
Especially in steel.
Yeah, but the technology has the ability to measure within that 2 millimeter range. As environmental things change, then you have to be careful about how you control that.
Is that good for the industry? I don't know what.
2 mil on structural is fine.
Yeah.
Pretty good. 3 millimeters quite typically $1, plus minus 3 millimeters.
I mean, those are all real examples, so those people wouldn't be using it unless it was meeting their specification.
That's a complex assembly though.
Yeah, yeah, exactly, yeah. Yeah, this one here. So you can see it's quite long, so they would need to make sure that they are careful with their control. Yeah.
Say, for example, we have like segmented assemblies,
Yeah.
which human beings should basically weld them or assemble them manually.
Mhm.
Have you used in any of your projects like scanning the entire assembly, getting the point clouds, mapping that point cloud with the already built CAD model, and
Yeah.
measure the fabrication imperfection?
Yes, so this first one I showed you is a good example, quite a relatively large structure. That's exactly what they're doing. Yeah, before they even move that structure, they take some measurements with the tile station, but primarily they're 3D scanning the whole thing and comparing it to the 3D model. And they're not moving it until they're satisfied.
I know that was like a config project, but
Yep.
do you have any numbers of that fabrication imperfection, like kind of making a comparison between the point cloud and the CAD model in order of like millimeter, centimeter?
Oh,
Because that becomes structurally an issue, right?
yeah, yeah.
Like if you want to talk about like P-delta and things of like geometric nonlinearity,
Yeah, yeah.
that will become an issue.
Yeah, I mean, the difficulty is, say, things like steel, they expanding and contracting throughout the day. So it's important that in that case, you're probably taking some constant measurements, but you have to allow for those changes to happen. So when you go to put it in place, if it's in the middle of the day or the middle of the night, there's going to be a big difference between what's happening with the steel. We see that on buildings a lot, like the sun moving from one side of the building to the next side of the building. And we see the expansion and contraction when we measure it with these technologies, in fact.
My research is very similar, but I'm working with timber.
Yeah, timber, yeah.
It's whole another like, issues in terms of humidity.
Humidity, yeah, exactly. Yes.
So the projects that we discussed were mostly for prefabrication and industrial work.
Yeah.
In terms of a more commercial project or residential project, is it
Yeah.
worth it to use this kind of technology when we have BIM models that are not so precise to be able to
Yeah.
catch that 3 millimeter difference?
Yeah, so normal construction, I would say this is normal construction in this situation, and also even in normal housing construction. Things like total stations are used every day on those type of jobs. More and more people for large buildings are using 3D scanning technology, but certainly from small to large, they're using the technologies. And the great thing about that is you can take, since more and more people are using 3D design, you can take that into the field with you rather than have a host of plans to work from. But you can also take a 2D digital plan into that environment as well and just use, a digital PDF to do it as well.
Would it be worth it if the BIM model itself is not as detailed or precise?
You're working with the data that you have, and so it's compared to using I would say a string and tape measure or plumb bob, using this technology is going to be far more, it's going to be more accurate. I mean, on a building like this, just putting in, all the components into place. We have one customer, actually it was working on a hospital here in Canada. I forget exactly where it was. Compared to using a manual method, placing all the components on one of the decks, they generally had about 75% of completion rate of putting components in the right place. Using a robotic tool station, they moved that up to 95%. So just to show you that, you know, being able to do that makes it more efficient. Yeah.
So the tool stations versus the 3D scanning, what is the accuracy? How do they compare?
So if at short range, say, let's talk ranges up to say 30 meters, then the accuracies are very comparable. When you start to get over that range, then with 3D scanning, it tends to vary a lot more. Just because you have environmental comparisons, you're collecting a lot of data really fast. So up to that sort of 30-meter range, then I can compare the both. Depending on what you want to map and what you want to compare it to, so then you would have to move the total station, the scanner further. The total station you can measure over a lot longer distance before moving it to the next location to maintain accuracy.
And within the 30 meters, it's still within a couple of millimeters.
Yep. Exactly, yeah. Okay, great. Thank you so much. I appreciate it.